Hi everyone, my name is Onat Dalmaz. Here, me and my friends Hasan, Atakan, Bedel and Usama Mirza are going to present our medical imaging course project, which is MRI simulation. Because of its superior soft tissue contrast, magnetic resonance imaging or MRI is the preferred modality in clinical neuroimaging. Its capability to capture the anatomy under a variety of different contrasts allow it to gather additional diagnostic information over the course of an exam. Furthermore, different from radiography-based imaging systems such as X-ray and CT, MRI scans do not expose subjects to ionizing radiation. Here you can see an overview of the user interface of our simulator. The user can choose various contrasts, slices, slice thicknesses, pulse sequences, and non-ideality conditions. The simulator then performs the imaging of the anatomical brain model with the given options. For contrast, we considered T1, T2, and PD weighted images. We performed imaging with gradient and spin echo pulse sequences. We also considered the effect of chemical shift, T2 decay, proton density, and B0 variation. For our dataset, we used BrainMap dataset, which can be accessed through this link. We considered a discrete anatomical model of a brain, which comprises 1 mm cube isotropic voxel grids with dimensions 181 times 217 by 181.
Hi, I am Hasan Bedel, and I will continue from here. I'm going to talk about the methods that we used. There are three main sections. The first one is slice excitation, and the second is case-based sampling, and the third one is image reconstruction. We have to excite the slice because we are not taking Fourier transform in 3 dimensions, but in 2 dimensions, so we have to process the whole stuff in a slice-by-slice manner. So in order to do that, we have to excite one slice, the particular thickness. In our simulations, we used the ideal excitation formula here, but a more realistic one will be something similar to the right-hand side. It is the convolved version of the reg function with a sinc function. In order to simplify our analysis, we did not consider the realistic excitation. Okay, so in order to form the image, we have to sample from case space, and how we do is kind of illustrated in the left part. There is a RF coil, and the signals coming from the X and Y points are accumulated at the coil. On the right-hand side, you see the equation for this. It is the double integral of the magnitude of the magnetization at that X and Y point, and some E to the values. And basically, for us to simulate this, we have to take the double summation because we are working on a discrete. We are working with discrete elements, and the end formula gives us a nice formula for the case space sampling. We take the 2D Fourier transform of a signal given in the equation, and as the time passes, the points that we sample from the case space changes. So this is very convenient. The T2 and T2 stars are selected based on the echo mechanism that you use to generate echoes. If gradient echo is used, then we use T2 star here. And if the spin echo is used, then we use the directed T2 values. And there's a nice illustration why this is the case. If gradient echo is used, we start to sample right after the first RF pulse. And the dominant decaying is T2 star. And at right-hand side, the spin echo is illustrated. We start the sample after the 2 times value of the first, second 180-degree RF pulse. So during this time, the sampling time, the T2 decay is prominent. So that is why we use different time constants. in this formula. And we have different contrast mechanisms. As you can see in this formula, we have lots of degrees of freedoms. And one of them is TR, and the second one is TE. And based on what we want to amplify, we change TR and TE values. If we want to show the proton density, then we should ignore the T1 and T2's effect. And to do that, the TR should be much greater than T1 and TE should be much greater than T2. And similarly, for T1 and T2 weights, we change the T1 and T2, TR and TE values based on the target contrast mechanism. And as you can see here, we employ a basic Fourier inverse transform to construct our beautiful MR image from the case space.
I'm Usama Mirza, and I will be presenting our results. We have tested our simulator by checking the effects of the following parameters on the reconstructed image. To test their effect, we varied these parameters one by one while keeping everything else fixed. We took the spin echo images of the same slice with T1, T2, and TD weighted contrasts. In our model's output, the three main types of tissues in our brains, white matter, gray matter, and CSF, all show different intensities under different contrasts and are easily distinguishable. We then took the gradient echo images of the same slice with T1 and T2 star weighted contrast. In our output, the different types of tissues showed different intensities and were easy to distinguish. We have learned that in MRI, only 1 part per million variation of the field is allowed in each millimeter cube. Therefore, we have added Gaussian noise with mean 0 and variance 1.5 microtesla to each voxel. Our output shows that the images reconstructed with noise added are more realistic. We know that T2 decay is the main source of contrast in MRI images. We tested our simulator with and without T2 decay, and we can see that the image with T2 decay has better contrast, while the image without it is more black and white. Chemical shift is the change in Larmor frequency of hydrogen atoms when they interact with different types of bonds in fat structures. We ran our model with and without chemical shift. On close inspection of the output, it can be seen that adding chemical shift causes a slight spatial shift in the image. Proton density also helps to improve the contrast of the MRI. The output of our simulator with and without proton density clearly shows that the image with proton density has much better contrast. Without proton density, it is almost impossible to differentiate between the types of tissues. During computation, our simulator reconstructs image of thickness 1 millimeter and averages them to get the result of any desired thickness. The averaging of images decreases the resolution and increases the blur in the resulting image. Our simulator's output shows how the blur increases with increasing thickness.
Thank you for listening to us. Now we will give a demonstration of our application. Here we have the parameters. So for fast imaging, let's keep the thickness of the slice at 1 millimeters. Select an arbitrary slice. Let's keep it spin echo pulse sequence and get a T1 weighted image with all of the non-idealities. Now it's computing K-space for the image. Once the K-space data is acquired, it will reconstruct the MRI image. Here you can see both K-space data and reconstructed image. Thank you.